Hi there, Physics First students. To get started in our coding adventures here in physics, we're going to need to download a piece of software and get that installed on your machines. We're going to do that right now. Let's go ahead and do a search for Arduino download. And then you're looking for Arduino Home, this Arduino CC, or you can just go straight to the source. Okay, and then depending on what operating system you use, just download the correct one for you. It should only take a few minutes. Just install it with all the defaults. Something else you're going to need to not install but to log into is this thing called Tinkercad. Okay, so tinkercad.com. If you'll set up an account, it's a free account. Please set up one that's personal. Do not set up a classroom account. Do not set up a classroom account. Just set up one that's personal to you. You can use your school email or you can use your personal email. If you use your personal email, it will travel with you after you graduate from school. So let's get into Tinkercad right now. So once we're in Tinkercad, we're going to click on Circuits. Okay, and here are all my circuits that I've created, or some of the circuits I've created. And we're going to click this green button here to create a new circuit. Now in this class, you might have used this to work with your circuits in that section of curriculum. But here we're not going to actually build a circuit. We are going to put this little guy on, scroll down under Basic Components and find the Arduino Uno. This is a microcontroller, okay? And we're going to put this virtual microcontroller on the desktop here, and we're going to be able to write code for this. So in the classroom, we're going to write code for an actual microcontroller. It's going to look just like this one, or very similar to it. And we're going to write code in that Arduino software, the IDE, right here, the Integrated Development Environment. We're going to be writing code for the actual device with this piece of software, but we could simulate that over here in Tinkercad. And before we get going any further, once we've dropped the Arduino Uno, this microcontroller, onto our desktop, let's change the name of our file here. So I'm going to call it Physics First Kinematics 1. Okay, just in case we want to come back and do a second or third kinematics piece of coding. So if you recall the kinematics equations from physics, these are probably the first sets of equations that you might have used in the physics class. For example, these are what I'm talking about here. Primarily, we're going to be dealing with these first couple here. If you're not familiar with this, just know that we'll discuss it when we get there, but hopefully everybody is familiar with these and these variables: final velocity, acceleration, time, initial velocity, and this delta x is displacement. So we're going to start writing code for that, but in a few minutes. But for right now, let's just learn kind of our way around the microcontroller. All right, so we're back here in Tinkercad, and we renamed it, and we're going to open up the code window. And some might be familiar with this block notation or blocky notation. And this is a way that you can write code without having to actually write code. You can kind of pull things in and set it up like that. We're not going to actually do any of that here. What we want to do is we want to convert this to text. Okay, so I'm choosing blocks here. I'm going to get rid of that and go to text. I'm going to say continue. This is a piece of simple code. And we can test that. We can start the simulation. If we look over here, this little L, which stands for LED, that little guy will start blinking. When we run the simulation, the programming cable will get simulated, plugging into the microcontroller, and you can see this piece of code here will write code to the microcontroller, and that will turn the LED on and off. All right, this is the default that gets started. I'm just going to delete everything here. Okay. And notice I'm leaving these two, what are called functions, the setup function and the void loop function. The setup function has a curly brace that starts it and a curly brace that ends it, and the loop, the same thing. Curly brace that starts, curly brace that ends. So you can't get rid of those. Those have to stay. And Arduino forces you to keep both of these functions, the setup function and the loop function. You have to have those two functions in all of the Arduino programs, or what Arduino calls sketches. All these Arduino sketches have to have these two functions. Okay? At the very top, we're going to, so I've entered a few lines, we're going to add a comment here. And comments can come in two different flavors, two different ways we can add comments. One way is to use the // Okay, this is the symbol under the question mark. Okay, And what we usually do is we comment what the name of our program is. So in our case, it's physics first, kinematics, and then 1. And it has an extension of INO, so .INO. And then we usually put our name. And we usually put the date. And the date here is 3/27. So that's one way to put a comment, and the computer will ignore, the compiler will ignore anything after the double slashes. You can also put a comment that is a bit longer. If you wanted to put up what's called a comment block, and you do that with a /* and then you hit enter a couple of times and then do */, and that will allow you to type anything you want to in here. For example, we might want to put a little description of our code, and I've copied and pasted from another document. And so this allows us to comment a block of code that the computer will ignore. And comments are really there for human consumption. All right. For example, we might want to also put inside the void setup in here that this function runs forever. Runs once. This setup runs only once. Okay. And the loop function runs forever. Okay. And this will loop over and over and over again. So anything we put inside the loop function will run multiple times. Anything we put inside the setup function will run once. All right. So there's a command that we are almost always going to use in setup, and it's called serial.begin. Okay. And it needs what's called an argument. It needs a number to be sent to that command. Okay. So notice carefully here the spelling and the capitalization. The S in serial is capitalized. Every other letter is lowercase. And then we have a parenthesis with the number 9600 and a semicolon. Okay, so let's kind of unpack this. The semicolon marks the end of lines of code. The serial represents the serial monitor, and the word begin tells it to open the serial monitor. Okay, so we might put a little comment here to remind us what this does. It's required, right, to open the serial monitor. The number, the argument that's inside the parentheses, this 9600 number, is what's called the baud rate. This tells the computer how quickly to communicate between the microcontroller and the serial monitor. And you don't really need to know anything more than that. Just as a frequency with which the microcontroller and the computer monitor are going to communicate. And this line is just basically magic. And so after that line, you can hit enter. And then sometimes it's kind of nice, it's to put a little delay, a 100 millisecond delay, to allow time for the serial monitor to open. So this pauses the program, pauses the sketch for 100 milliseconds. And you hopefully know that that's 0.1 seconds. Okay, to fully open. And this just comes from experience. It's not necessary to put this in. You may not all need it, but some students will have a computer that's a little bit slower than others, and so the 100 millisecond delay just gives everybody time to have all of their serial monitors open. All right. So far this is done. We've done nothing really that we can see. The serial begin happens, is kind of invisible, and so is the delay. I want to make sure that we're putting all of our code right now within these two curly braces. Okay, make sure that's in between the two curly braces. Okay. All right. Let's add a line of code here, and let's say hello to each other. So again, we're going to be working with the serial monitor. So serial, right? Capital S, and then we're going to do .print. And parentheses, and then anything you want to put in quotes is fine if it's, appropriate. Okay, anything within the quotation marks will be printed to the screen. And because we're at the end of our line of code, we're going to put a little semicolon there. Okay, So this will print or display to the serial monitor anything that we have enclosed in quotation marks. This thing in quotes is called a string. It's a string of characters. Okay, and in computer science, we call these things strings. And so there's the character H and the character E and the character L and so on. And so you put together a string of characters, sort of like you're threading, Cheerios onto a string to make a necklace. You're stringing together these characters to print it out to the screen. So let's take a look at that right now. So we're going to run the simulation. If you've typed it in exactly like I've typed it in, then you should not get any errors. But if you do get some errors, pause right now and just make sure that your S's are capitalized and your quotes are here and your semicolons are there. Make sure that all of your code is within the setup curly brace loop. Make sure that you haven't deleted the curly brace loop accidentally or something like that. Okay? All right, to see this printing to the screen, we have to open the serial monitor, which is down here. All right, and so there it goes. So we open it, it says hello, and we see that it has done exactly what we say, print hello. Okay. So let's keep going. Let's stop the simulation, and let's add another line of code. We'll come back and add comments in just a minute. Okay, let's do another print statement. And let's say welcome. Or something like that. Again, has to be enclosed in quotations. And we're going to close it with a semicolon there. Okay, so let's see what happens now. We can clear the screen if we want to get rid of that so we can see it fresh. We run start simulation. And it prints hello, and then it also prints welcome to Physics First Coding. Okay, now notice that butts up right next to each other. So we can deduce something here about print statements. Print will print a string to the screen, and it will keep the cursor at the end of that line. So when we print the next string, it follows right along there. If we want hello and welcome to be separated a little bit, what we have to do is stop the sim, increase our spaces here, restart the simulation, and now you can see that it's going to give a little bit of space there. We can clear it and start again if we want to. So there, now we have some space. Okay? All right, so let's stop the simulation and let's add a comment here. Okay, just to remind us what we're doing. So this sends the hello string to the serial monitor. Okay, that's what that print statement does. And the same is true for the welcome. Sends the welcome string to the serial monitor. Let's add a command, or let's add another line down here that seems very similar. This time it's serial.println, LN. Okay, that stands for a line feed. And our message here is, I'm happy to be with you, or something like that. Or I'm happy you're here, or something like that. Okay? All right, let's take a look, and then let's add one more line. Okay, another serial.println. And it says something like, I don't know, today we will do some kinematics coding, or something like that. So let's clear the screen and let's see what happens when we run this. Notice the difference. The only difference here is I've added the addition of the LN. That's an L, not a 1, LN. Okay. So it prints hello, it prints welcome, and then on that same line it prints I'm happy to be with you. If we wanted to, again, if that's lack of spacing there bothers you, we can add some spacing here. So prints hello, it prints welcome, it prints I'm happy, and then look at this. Today we will code some kinematics. Misspelled that, or didn't put the we in there. But notice that that's on another line. That's because when it read this line here, not only did it print the string to the screen, it also gave what's called a line feed, or a return key, or an enter key was pressed, pretend pressed. And so here, when you print, it prints the thing and then gives a line feed to send it to the next line. Okay? And so that's what happened here as well. So it printed today, we will code kinematics, and then it sends it down to the next line. And so those are the two ways we can display information to the screen, print and println, and you'll see when we use one and when we use the other. We add that in there. All right, and just to kind of see what's going on, what we can do is we can pause all of this. Okay, so we can print hello, give a pause for 1,000 milliseconds, which is of course 1 second. We can pause after that one. I'm just copying and pasting there. We can pause after that one if we'd like to. Clear the screen and start the simulation and watch what happens now. So hello, and then welcome, and then I'm happy, and then today we will. And so in this way we can see the action of the code by just slowing it down a little bit and letting the human see what's going on. All right. I want to end coding for the setup inside the setup function here, and I want you to see what happens when we code inside the loop function. So let's add a new line here inside the loop. And again, the loop function runs forever and ever and ever. So let's just say let's get started or something like that. Serial.println. And then let's print a little spacer there. Just, you know, little pizzazz. Okay, so let's see what happens now. I'm going to clear the screen, start the simulation. Hello, welcome, I'm happy, today we'll get started, and let's get started, let's get started, let's get started. Okay, so this is going to run forever and ever because that loop, when it hits this bottom curly brace, is going to bounce back to the top curly brace and start all over again. Okay, so if we stop the simulation, we can slow this down a little bit. Again, at a 1,000 millisecond delay, perhaps clear the screen, rerun it. I'm going to make my serial monitor a little bigger here. Can I do that? Yeah. So let's start the sim. All right, so it says, let's get started, let's get started. Our situation today, we don't really need to do that. We don't need to keep saying, let's get started, let's get started. We only need to say it once, right? And so what we can do is we can get rid of this delay if we want to. Come down to the bottom. Again, please make sure that you're within the bottom curly brace. If you don't, you're going to get an error message. And I'm going to come down to the very bottom here. I'm going to type this command right here. While true. Okay. And yeah, let's just run and see this. See what happens here. I'm going to clear the screen. Hello, welcome. Happy to be with you. Let's get started. And notice it only does it one time. Okay. The loop still runs forever, but when you get down here to line 34, this particular line right there is what's called a while loop. And the while loop is one of the looping structures in all coding languages. And this will run while a conditional expression is true. And so, for example, you might want to say in here, while 1 equals 1. Okay, and this equals is a conditional expression equals, like while 1 is equivalent to 1. And so that's also true, right? Is 1 equal to 1? Yes, it is. So it's true. So that loop will run forever and ever and ever. The easiest way to say this is just while true. If we get rid of this little semicolon there and rather add a curly brace, okay, add a curly brace there and a curly brace there, and go inside the curly braces, we can print something inside of here. So this is now a while true block. And so, for example, we can do serial.println, quote, do nothing. Uh-oh. Okay, and maybe have a little delay in there just so we can see it. Maybe 500 delay. Okay, and you can see that when we start the simulation, clear the screen. So that while true statement is just running over and over and over. It's printing do nothing, do nothing, do nothing, do nothing. All right, so stop the simulation, and all of this can just be simplified. You can leave it like this if you want to. I'm going to just get rid of it and put it back to the semicolon there. And maybe put a little comment that says pause program forever. Okay, so that pauses the loop function. This guy here will just run forever and ever and ever. Again, if we clear it, start the simulation, you can see that let's get started is only going to print once. Okay, and at this time, I don't want to have to wait for hello and welcome and all this to get printed. So we could either make these delays be smaller, or simply we can comment out the delays. Just put a little comment block or comment line in front of each one, and that tells the controller, just ignore those. It will then run hello, welcome, I'm happy today really fast. Okay, and so let's see what happens here. Just to, sanity check. It's going to go fast. Boom, boom, boom. Okay, so let's get started. We're going to start adding code right down in here. That's going to turn the microcontroller into a calculator. Specifically, we're going to have it solve physics problems for us. Okay, so let's take a look at our first problem. A car is traveling with some initial speed of 7 meters per second. It accelerates at a rate of 2.5 meters per second squared, and the time is 4.6 seconds. So the two questions are, what is the final speed of the car after 4.6 seconds, and how far does that car travel during that time period? So I've got a sheet of paper here, and I've got the physics equations that we can look at. So let's take a look at, I'm going to close the serial monitor so we can see the problem. So we have the initial velocity, which is vi, we have the acceleration, which is a, we have the time, which is t, and we're looking for the final speed, which is vf. So this first equation right here is going to really do the trick for us, I think. V is equal to at plus vi. And so, well, what is a? So this is how I would define this. This is bad physics. And what I mean, you'll see what I mean by that in just a second. So we see that v final is equal to a, which is 2.5, and times the time, times t, 4.6. And then we're going to add in the initial velocity plus 7.0. Okay, I think this is not the way to solve a problem for lots of reasons. So we grab our calculator, we type that in, and we just simply do it as a math problem, 18.5. So our answer is 18.5. I don't like this for many things, not least of which is there are no units here, there are no variables that are used, there's no equation that we can see, it just is a bunch of math, right? This is not a math class, this is a physics class. So, but nevertheless, this is how you would do the calculation. So this is some bad physics. Let's see how to do it as a calculation using some bad code. Okay, so again, I'm going to kind of keep this over here so we remind ourselves. And I'm going to write code right down here. So I've added this problem. Feel free to add it or don't to your sketch if you want to or not. It's up to you. Okay. So what we would do is we could just treat this like a calculator. The microcontroller is really, it can be treated as a calculator. And so, for example, we can just simply print the answer, serial.println, all right? And then we can just do the math. So a is 2.5, and then we want to say times, and so in computer speak you would do the times as the asterisk, which is shift 8, 2.5 times, and then the t is 4.6 seconds. All right, so that takes care of the at part of our equation, and then we need to add in plus vi 7.0. Do a little semicolon there. And then we can start the simulation. We can open our serial monitor and look at that. So it prints the answer 18.5, and if we come back here to our little calculator, we see that that is in fact the case, also 18.5. So calculator and computer seems to be in agreement. But this again is what I consider some bad physics and some bad coding. So I'm going to stop this simulation. I'm going to remind myself that this is really bad. That needs to be a comment. But it does get the point across that you can do mathematics on the microcontroller. Surprise, surprise. Let's take a look at what good coding looks like. And then before we do that, let's take a look at what good physics looks like. All right, hopefully we can see this all on one page. Let's see here. So this is some good physics. Or some better physics, at least. So the first thing we want to start with are some knowns, right? Some variables. So we are told that the initial velocity is 7.0, and we want to use units, meters per second. We're told that the acceleration is 2.5 meters per second squared. We're told that the time is 4.6 seconds, right? And so those are our knowns. That's what we've written down as our knowns. And then our unknowns here, the things we're looking for the final velocity, and we're looking for also how far does the car travel. We're looking for its displacement. And we're going to just assume for the displacement argument that it starts at 0 meters. Okay, we want to see what it's like, what the displacement is during those 4.6 seconds. All right, so with good physics, we would write down the variables. We would also write down what the equations are. So the first equation is V final is equal to AT plus V initial. And that's how we're going to solve this guy. So what we would do is we'd write down the equation, then we would plug in our values, okay, and you would write 2.5 meters per second squared, or at least my students better write down meters per second squared. I don't know how the other teachers in the group feel about that, but I think it's important to put units down. And then plus the initial is 7.0 meters per second. All right. So now when you do the mathematics, it's going to be the same answer up here that we got up here. It's going to still be 18.5, but the units tell us if we got the right answer or not from dimensional analysis. So meters per second squared times a second, one of those seconds is going to drop off. You're going to get meters per second. And that allows us to add meters per second to meters per second. And so meters per second plus meters per second is meters per second. So dimensional analysis is correct. And it's, seems like we got the right answer here, 18.5. Let's see how we would go about coding that in right now. Okay, so in the computer world, we have these things called variables, just like we have them in math, but we have to tell the computer what the data type is. And so data types can be anything from integers to strings to bytes. And there are these things called floating points, floating point numbers. And, an integer is a number that is like -3 or 2 or 0 or 5. These are all integer values. A floating point number floats between two integers. For example, pi is 3.14, and that floats between the integer 3 and it floats between the integer 4. And so we call these decimal numbers floating point numbers. In computer science, we will define our variables using one of these data types. Typically, if you're doing math, you can define it as a floating point number, or more simply, as a float, F-L-O-A-T. And so that creates, that's going to help us create or tell the computer, hey, we want to create a variable. Okay, so let's name our variable, and let's call it VI. And that's it. So we've just created this variable, this initial velocity variable, VI. And we might want to put a little comment here to tell the programmers who come behind us what this is. Initial velocity variable. Okay, we're going to do the same thing for the acceleration. Let's just call it A. That makes sense, right? Because that's what the equation uses, right? And I should be more specific here. This is the creation, create. We're creating the initial velocity variable. We are creating the acceleration variable. And we're going to create the time variable, t. Again, float stands for floating point number. Now, we can also go ahead here and we can create a final velocity variable. and we can create our displacement variable. I'm just going to call it x. I know it's delta x. X is really position, but for the sake of simplicity, let's just call this displacement. If you recall, displacement is x final minus x initial. And so if x initial is 0, then maybe x final is probably a little bit better. So our final position, or I'm just going to leave it as x and make that be displacement. So let's don't get too much into the weeds with physics. Talk more about coding. All right, and so just like we did over here on paper, we're going to do the same thing over here. VI equals 7.0. Now, you can't put units on a number here because this is a floating point number and units are strings, but we can put them as comments. Units meters per second. Okay, we can do the same thing for our known value for acceleration, 2.5. And don't forget the semicolons, and that's in meters per second squared. And we could just do the caret 2, right? And then time, I think, was 4.6 seconds, yes. So one thing that I forgot to do that I should have done at the beginning is to put a little comment here. For example, populate the input variables. Okay, so we're going to give them numbers, and we also note the units. Okay, so that's just a little directing traffic with our comment statement. All right, so what we could do now is we could calculate the final velocity, but I think it's really important, I tell all my students this, that it's also important to echo to the screen your input variables to make sure that your values are correct. And there are a couple of ways to do this. Okay, so I'm going to put a little comment here. Echo the input variables. And so let's echo the initial velocity. So we could just simply do this. We could just serial.println. We could just serial.println the initial velocity. And we could do the same for the acceleration. We could do the same for the time. I mean, let's do that. Let's see what happens if I'm going a little off script here. I may regret it, but let's see what happens, okay? I'm going to clear the screen. I'm going to start the simulation. Hey, there they are. There's the initial velocity. There's the acceleration. There's the time, but it's a little cryptic, right? We can't really see exactly what's going on here. If somebody walked into the room, somebody who even knew physics, they wouldn't be able to look at these numbers and go, oh, I know what they are. So this is probably not the way I would do this. I'm going to get rid of those lines there. And what I want to do is I want to echo words that make sense to the humans who are going to be using our sketch. Serial.print, print. So I'm going to do serial.print, and I'm going to type initial velocity equals, and then I'm going to close that. So I'm going to print that, and notice it's print. I'm going to change this println to print VI, and I'm going to come in and add the units. And because this is the last thing I want to do on this line, I'm going to use println. Can't type. And then the units will be meters per second. Something like that. Don't forget to close the quotes. Don't forget the semicolons. So now if we start this, I'm going to clear and start the simulation. Now this is very readable, right? The initial velocity is 7.0 meters per second. Very nice. Let's do it again for the acceleration for the time. So what we could do is we could just copy these 3 lines of code, paste, paste, paste. So let's do that now. Let's stop the simulation. Copy these 3 lines here, maybe with a blank line in between just to offset it. Copy, paste for the acceleration, and paste for the time. So let's change this to acceleration. Let's change this variable to acceleration, the A, and let's change the unit meters per second squared. And then let's do the same here for the time. The variable is T, if you recall, and of course the units for time, seconds. So let's see what happens here. Maybe let's clear the screen, start the simulation. All right, and so now this is very clear. Initial velocity, acceleration, and time are all printed with units and the numbers, super easy to read and decipher. Let's now calculate the answers. Let's calculate the final velocity. Let's calculate the displacement. So perhaps we can do a little something fancy like this, just to offset the input variables from the output variables. Okay, just something like that. And maybe a little comment. Now let's calculate the the answers or whatever, the output. Okay, so if you recall, the final velocity is a times t plus the initial velocity. And we've created the final velocity variable, so all we have to do now down here is to set it equal to this equation here. Okay, and so final velocity is equal to the acceleration times the time. Remember, we have to do the asterisk multiply, plus VI. Now notice I had typed capital VI because it's just kind of a habit of mine, but when I define the variable, it's lowercase vi, so I have to do it exactly like I entered it. So this has to be lowercase vi, and at the end of the line, I have to put a little semicolon to say we're done, and maybe a comment. And what we can do to print this is we can grab this line, for example, these 3 lines, okay, and we can print them. But instead of the initial velocity, it's final velocity. Instead of VI, it's VF, and of course the units are the same. All right, so let's see if that works. All righty, let me stretch this up a tiny bit. Let's see here. All right, so I've got the initial velocity, the acceleration, the time, like before. I have my little offset, and then the final velocity is, in fact, done for us. That's pretty nifty, you ask me. Okay, and now what we have to do is we have to now figure out what the displacement is. So if we take a look at this equation, for example, the displacement's 1/2 at squared plus vit. We know all the information here. We also know this information down here as well. But it's probably not good to use something we just calculated. It's better to use the 3 knowns that we have. So on paper, we would write, delta x, or in our case, remember this is just x. 1/2 at squared, always write down the equation, plus vit. Okay, and now we plug in our numbers. 1/2 a is 2.5 meters per second squared. Our time is 4.6 seconds. Don't forget to square it, plus VIT. This is going to be our 7.0 meters per second times 4.6 seconds. Okay, so that's what it looks like on paper. Let's do the calculation. So typing that into the calculator should give us something like 58.65. And again, we can look at our units, dimensional analysis, meters over second squared. Second squared is second squared, so those seconds cross out. Meters over seconds times seconds, that crosses out. We're left with meters plus meters, meters. Okay, so again, the whole reason we use units there. And so let's see if we don't get the same answer when we code it in. So I should, you guys can probably figure this out on your own. This t squared is something we'll talk about, but you know what t squared is. 1/2, which is 0.5, and then a, and then t squared is like t times t. So that's one way to do it. I'll show you a couple of ways to solve this problem here. Okay, so I'm going to stop the simulation, and I'm going to do it myself as well. X, that's our variable that we defined. I'm going to use 0.5 times a times t times t. So that's t squared, right? 1/2 at squared plus vi times t. Okay, and then, again, I'm just going to copy this. And I'm going to paste this. And this is going to be our displacement. And this is our x. And our unit is in meters. So let's run the sim and see if we don't get the right answer. What did I do wrong? I missed a semicolon somewhere. Oh, there it is right there. It tells you that there's a problem with the void loop. Turns out I forgot the semicolon right there. Okay. Maybe you were screaming at the screen, in which case that's great. So we just put that in, no big deal. We have to open up the serial monitor once again. So final velocity and our displacement, let's see, does that match? Hey, so maybe our physics is wrong, but at least our calculations are correct, 58.65. All right, I want to talk a bit about this equation right here. So there's another way to do this equation, and I'm just going to copy it, paste it. And instead of doing t times t, we can use the POW command, P-O-W. This stands for power, okay, and it has a parentheses, and it needs two arguments, what are called arguments. So one is the base, which is t, and then the other is the exponent, which is 2. So that's going to be t squared. So that raises t to the power of 2. And we could just let it recalculate it twice, calculate it once, and calculate it again. Or we could comment out that line and leave it there as a little tutorial for us. So let's see if this works as well. So now I'm not running the original line, but I'm running the POW line. And look at that, same answer. Okay. I want to further go deeper into this line, so I'm going to copy this and paste it. And I'm going to comment out the original, again, to leave it as a little tutorial. And this is going to be weird, okay? So we could do 1/2, 1 divided by 2, okay? So the computer can do division, of course, just like it does addition and subtraction and multiplication. So 1/2. So let's look at this. This is actually weird, and it's weird for this particular language. If you did this in Python, it would actually be fine. But with the Arduino C language, let's take a look at what this looks like. Okay. And our displacement is 32.2, not the same thing we've been getting. Okay. That is because 1 divided by 2 is the computer is doing what's called integer division. Okay, and 1 divided by 2 is 0.5, of course. And when the computer in Arduino C does integer division, it truncates the variable. So 1/2 is on the calculator, right, is 0.5. It gets rid of the decimal when it does integer division. It looks at this and goes, oh, 1's an integer, 2's an integer. My human wants me to do integer division. And so I'm going to put a little comment here. And obviously it gives us the wrong answer because 0 plus VIT is what we're really doing. So I'm going to put a little comment, beware of integer division. So how do we fix that? Well, one way, of course, is to use the 0.5. All right. I'm going to just copy this, and you're going to see how we can fix it easily. I'm going to comment out that line. I'm going to paste it again. And if we want it to divide with floating numbers, we simply turn the 1 into a float and the 2 into a float. 1.0 divided by 2.0. This tells the processor that, hey, we need this to be floating point numbers. So let's take a look now. There it is, back to normal. So personally, I think either one of these two lines up here is the way I would go with it. If you're just doing, t squared, then t times t is perfectly fine. You wouldn't want to do t times t times t times t if you're doing like t to the 12th power, for example. You would just change it to 12 right there. So that would be an easy thing to do with the POW command. So there are lots of things, lots of ways to solve problems with coding. And your teacher, your boss, people in your team that you work with will have a way that they prefer, and you will have a way that you prefer to do it. But you can put your little individual touches there. But for now, I think we can leave them here as a little tutorial for yourself. So that's the gist of doing mathematics with a microcontroller or even a desktop computer. This language, Arduino C, is identical to C. So what you can do on a microcontroller like the Arduino, you can do on a desktop computer. There's some small syntax changes, but primarily it's basically the same. So some of you may be asking, why bother with coding, for you really could have done all of this calculation so much faster with your handheld calculator. Okay, so let's solve another problem. I'm going to stop the simulation and let me paste another problem here. Boom. So let's have a race, okay? So imagine the car is now moving with the speed of 25.3 meters per second, so a little faster. But now it runs out of gas, and the car is going to slow down at a rate of 1.5 meters per second squared. So that's the deceleration of the car. What will the car's speed be after 13 seconds, and how far will it travel during this 13-second period? Here, I'll show you what it looks like on paper. So on paper, it takes a long time, but even on the handheld calculator, you would have to, type all of these numbers in and do the calculations yourself. Okay? All right, so grab your calculator and let's race. All I have to do is scroll back up here to the top where I defined this. This is now 25.3. My acceleration is negative 1.5, okay, because it's decelerating. And my time is 13 seconds, 13.0 if you want to be exact. And I'm done. So I can start the simulation, and it's going to recalculate everything for me. Boom, done. My guess is I beat you, even though I was talking and taking my time. Okay, but you should find that these are the correct answers. I hope you do. And so that kind of goes to show one reason the computer is really powerful. It's for making lots and lots of doing lots and lots of calculations. Okay. All right. So if you wanted to preserve both problems, what you could do is we could stop the simulation here, for example, and we can clean up our code. So this bad code is fine. Let's leave it, but let's comment it out. Again, a nice little tutorial. Here's our problem number 1. Okay, so I have copied a little thing like this. So this is going to print a blank line, and then it gives us these little stars here that tells us this is kinematics problem number 1. So if we put it back to the original, forget what the original was. So if you take a look here, the original was 7 and 2.5, and I think that was 7.0 seconds here. And of course, play around with this. Change any numbers that you want, have some fun with it. So if we were to run it now with this little kind of fancy header, so we get kinematics problem number 1. It looks kind of nifty. And if we wanted to preserve these, have both problems that show up, we can simply just copy. Well, let's see here. Probably we don't need to re-copy these guys here, because those have already, you can only create variables once. Okay, and in hindsight, I probably should have put this lower. But we'll just copy this, scroll to the very bottom after problem number 2, and stop the simulation. Okay, so this is going to be kinematics problem 2. And I can scroll up here and grab the input variables for problem number 2. There are more efficient ways of doing all of this, but for an introductory lesson, I think this is good enough. So this is going to populate the new input variables, 25.3, and then new acceleration is negative 1.5, and this was 13, I think. Okay, and so kinematics problem 2, let's see what that simulation looks like. So there's problem number 1, and there's problem number 2. And we preserve, that doesn't look right, does it? I felt the displacement here. This, what did I do? Oh, sorry, the time is 4.0. I forgot to change that. Okay. So 4.6. But you can see that even though I've made a mistake, right, it's super easy to fix. So there it is. So our displacement for the first part of the problem is here, and our final velocity is there for the first part, and then when the car runs out of gas, the final velocity and displacement for the second part. All right, so this is the end of this lesson. I do want to show you how the computer can be used in even more powerful ways, but I'm not going to give you a lesson on that. I'm just going to kind of show off some of the power, flex some of its muscle. Before I do that, I will leave you with this, and that you can solve just about any kind of physics problem that you want now, at least if you can do some basic arithmetic with it, which is what most of our introductory physics is anyway. So you've covered how to print material to the screen, print data to the screen. You've covered how to create variables, and the float variables are the variables that I would use to do any mathematics. Okay, if you want precision, you're going to want floating point precision and not integers. You know how to not only create a variable, but you can define it. Okay, you can set one equal, and then you've learned how to do some mathematics with the variables. And then finally, of course, you can print words and the variables to the screen. Okay, pretty powerful, pretty simple, but think about all of the ways that you can now use this little lesson to do your physics homework, your math homework, and so solving lots and lots of problems this way, I think will stretch your coding muscles. All right, so let me show you one last little bit of code that I'm not going to really explain in detail, but I'm just going to show you really why computers are super handy. Okay, let's do that now. Okay, so I've got a bunch of code here I'm going to paste, and we can take a really quick look at it. So this is really the power of the computer programming and the power of using computers to solve physics problems. For example, we're going to calculate a whole bunch of these problems, a whole bunch of these kinematics problems, going from 0 to, in this case, 20 seconds. Okay, so the first thing I do is I print the initial velocity, I print the acceleration, and then I set up the header of a little data table. So I'm going to have a column of time over here, a column of final velocities here, and a column of positions here, or displacements. Right, and here are our two equations that look familiar to you, I hope. Okay, that calculate the final velocity and calculate the displacement. And then I'm going to print the output, the time, the final velocity, and the position, or the displacement. So what's new is this line here, line 166, and this is what's called a for loop. So early on we talked about a while loop. This is a different kind of loop called a for loop. For loops typically run for a finite number of times. And without getting too deep into it, it's a loop that begins in this curly brace and ends at this curly brace. So everything inside of this will loop some number of times. So each loop has a counter, or each for loop has a counter, and in our case, it is the floating variable t, time. And we start time at 0, and time is going to go to 20 seconds, or to less than 20 seconds. We can make it be less than or equal to if we want it to go from 0 to 20 itself. And this little thing here is shorthand notation for saying, after you run the loop once, take the time variable, which starts off at 0, and add 1 to it. Increment time by 1. T++ is kind of shorthand notation for let's make it get bigger by 1. So the next time around, t will be 1, and then 2, and 3, and 4, and so on. This will continue to loop until we hit that conditional expression. So when time is no longer less than or equal to 20, then the loop will stop. Okay? But while time is between 0 and 20, the loop will run. All right, so let's take a look at the sim. Let's open up the serial monitor just to see what's happening here. Okay. All right, so the top part is problem 2. We didn't really, let's clear it and run it again. So there's problem 1, there's problem 2, and then this is the stuff that I've added just now. Okay, notice it's a data table. We print the initial velocity and the acceleration, and then the time, the final velocity, and the position are all calculated. If you recall, in our problem number 2, and this is the data for problem 2, 25.3 was the initial velocity and negative 1.5 was the acceleration. The time, if you recall, for problem number 2 was 13, and these are the correct answers. That's what we calculated. What this thing does is it calculates what the final velocity is and what the position is at times 0 seconds, 1, 2, 3, 4, 5, and so on. What's cool about this is, you can see that it's slowing down, right? You can see that the position is increasing. It increases a lot in the first second, and it increases less and less with each subsequent second because it's slowing down. That's the whole nature of acceleration. The velocity is getting slower and slower and slower, and we can see that here in between 16 and 17 seconds, the final velocity goes from a positive number, moving to the right, for example, to a negative number moving to the left. So we know it must pass through 0 here. So somewhere between 16 and 17 seconds, we know that this car is going to have to stop. So what we can do is we can change our counter here. We know it goes, we can still have it go from 0 to 20 seconds, but now instead of adding 1 second to the time, what we can do is we can add a fraction of a second. And that's done with a longer notation. T is equal to T plus 0.1. And in math class, this doesn't make any sense, right? T equals T. But in computer, what this says is the new T is equal to the old T plus some number, in this case 0.01. So the first T is 0, and so that's going to run 0. The next time around, T is going to be 0 plus 0.1. The next time around, it's going to be 0.1 plus 0.1, and so on and so on. So let's see what happens here. I'll open the serial monitor. This is going to be a lot more data, okay? 10 times more data. There's problem 1, there's problem 2. And now we can look at our times. It's increasing by tenths of seconds. So it's outputting. It's going to take a little bit of time for it to get to the 20. It usually doesn't take this long on a laptop or something like that. It wouldn't nearly go this slowly, but because we're running Tinkercad, this is a simulation, and so it's a simulated microcontroller, so you're going to have a lot of lag. All right, so now we can see here now it's between 16.8 and 16.9 seconds that it hit 0, that it stopped. And if you wanted to, of course, we can make the counter increment by even a smaller amount. But I think this gets the point across. So this is not a model, but it is it's kind of what we call a simulation. So let me show you a couple more cute little things here before we put this to rest. All right, so one of the things I want to show you before we put this away is I want to show you where you can find this code here, for example. If you go to Tinkercad, so you might have 1 or 2 of these things out there. I've got a whole bunch. And we can click on this little wheel here, the option wheel, go to properties, and I can turn this. The default is private, but I can make this public for everybody to see. Save the changes. And then if you were on Tinkercad and just wanted to find things, find me, you can search for Chris Odom under people, or you can do a search for PF, Physics First Kinematics, for example, and you can choose circuits. Okay, and I think it pops up over there, circuits like that. Choose circuits, and then do the search. Well, it was here just 1 second ago. Where did it go? Let's do Physics First 1. Okay, so there it is there. If you wanted to get into this, you can copy this Tinker if you want to. But you could also just look around and see what other people in the world have done with the word kinematics somewhere in their sketch. Kind of cool. There's a lot of material here. You can learn all kinds of stuff from Tinkercad. I think it's a great, great resource. So I wanted to show you that, and you could tinker it. I also wanted to show you how you can get the code we just wrote for the simulated Arduino into the real Arduino. So the real Arduino, the actual physical thing, looks something like this. Looks very similar to what's on your Tinker page there. And we can upload code to this guy. The cool thing about this is once it's uploaded, you can unplug it. Okay, you can send this, put it on a robot, give it to a friend, send it to the moon or whatever, and the code stays on the chip. So when you plug it back in again, it will run. Let me just walk you through the process of taking the code that you write on Tinkercad, this guy here, and putting it into the Arduino IDE. So the first thing we're going to do is open up the code window, and I'm just going to do Command A or Control A, and then you can either do Command C or Control C, or right click and go to copy. So I've copied all of the code that we've just been typing. I'm going to then open up the Arduino IDE, and that's maybe down here on your dock bar. You might want to do a search for Arduino or something. And so this is what the code window looks like. So I can highlight all of this and delete it, and then paste the thing we just copied. And it looks a little different, but it's not much different. The IDE is much more powerful than Tinkercad is, so you can do more things with it, but it's basically the same thing. So one thing you want to do probably is you want to save this in the right location. So I'm going to go ahead and do that now. Maybe I even make a physics folder, physics first folder. And then I think we called this physics first kinematics. Kinematics 1. So I can save that somewhere on my computer. Next, I want to make sure that my board is chosen. Arduino Uno board is chosen properly. Okay, and it is. And then I want to choose the correct port. Okay, on a PC, it's really easy. Okay, you go to Tools, you go to Port, and it's going to become 3 or 5 or 7 or something like that. It'll say Arduino Uno. You just click it, and now that means that your physical board is connected with a wire, a programming cable, USB cable, into your laptop, into some USB port. Okay. And on a Mac, you go to Tools, Port. It's going to be a whole bunch of weird letters and numbers, but you're looking for the words Arduino Uno. Okay, and you're going to click on whatever that says, whatever. There are going to be several of them here on the Mac. I just know that it's going to be blah, 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 Uno, Arduino Uno, something like that. So then once you're done with that, you can press the upload button, and that uploads, compiles the sketch. It's very important while it's compiling, while you see the progress bar and while you see the words compiling and uploading, you don't touch the microcontroller. Another thing to be really careful of, the bottom of the microcontroller, when it's powered, has a lot of these power pins, okay, that are accessible, power and ground. And if you were to lay it down on something metal, like a metal desk, aluminum foil, a candy wrapper, or even a metal pin top, something like this, or a paper clip or a staple even, you can short and ruin the board. So just be mindful of that. Okay. We've uploaded the code, it's done uploading, and now I can click this button here to open the serial monitor. And we can then see it run. You can still see it takes some time here to run as well. Printing takes a lot of time, but we can scroll up and we can see our code, just like we did on Tinkercad. Pretty nifty. Okay, and so that's that. That's how you can put it into the IDE, super easy. And then the last thing I want to show you is how to maybe take this data here that's printed here, and it's much easier to do from the IDE than it is to do from the Tinkercad web window, we can copy this data and we can put it into Excel and we can graph it. This is physics and we do want the whole physics experience, don't we? So without diving too deep into Excel, let's see how we can do that. So I'm going to open up the serial monitor. Okay, I'm going to copy, I don't know, maybe this line here, which gives us our initial information, and all of this stuff here as well. We can scroll down, or page down, copy all of that, just Command C, Control C, copy that. And then I'm going to open up Excel. What is going on here? How come things aren't working today? Oh my goodness. Okay. All right. So we're going to open up a blank worksheet, and so there we are. So come down a little bit maybe, and then I'm going to just paste what I just copied. All right. So what I can do for this data here, and we can muck around with this. This is just some text or whatever. We can play around with that at a later date. But what we can do here is this. If we look at it, this is one cell filled with 3 columns of data. And so you think, wow, that's going to take a long time to parse all of this into 3 separate columns, because even though it looks like it's in 3 columns, it's really 3 columns of data in each row. So what we can do is we can highlight this. We can really highlight the entire thing I just pasted in. we can highlight all of this here, okay, all of that first column of data. And then if you go to data and turn text to columns, you can say it's fixed width. That might be what we want to do, but you can also go to delimited and choose space. And you can see here, it's going to see the spaces and going to put them in the right columns. And then you can go to next and finish. And so boom, just like that, now we have our 3 pieces of data. Anyway, this is our time, this is our final velocity, and this is our position. And of course you could do, Alt-Enter to put the units, but underneath each one if you want to do something like that. I should have done it as I was typing. I am a physics teacher after all, I got to do it right. Okay, and then we could also display the initial acceleration and the initial velocity and the acceleration in their own cells as well if we want to do something like that. Okay, so what we can do here is make it look pretty. All right, we can center it, we can make borders around them all, we can turn that header bold and things like that. But more to the point is we could make graphs of final velocity versus time and position versus time. I'm just going to really quickly go through this. Hopefully you've seen this before or you know how to do it already or something like that. So here we go. It's much easier to do with the PC, I think, than a Mac. But here we go. We select the data, add a series. Our X values is going to be time. We have to scroll all the way down to grab all the times. Okay. And click that box, choose our Y values. Let's do velocity first. Final velocity, come on, there it is. Boom, say OK. We can name it if we want to. Okay, and look at that. And perhaps you've done this before, and perhaps you remember it. So this is velocity versus time of a simulated car out of gas, something like that. And we can go and add axis titles. This is our velocity, meters per second units, right? And this title down here is our time. And we can put variables in there if we wanted to as well. Hopefully you know something about this. You can see that it reaches 0 velocity between, looks like around 16 something seconds, right? And again, we can scroll down and look more carefully. We can fit a curve to this, a trend line, and go to more options if we want more than just the line itself. We can display the equation and the r squared value here. I can make it a little bit bigger. And if let's see here, we don't plot y. What are we plotting here? We're plotting velocity, and we're not plotting x. We're plotting time, t. So I guess we'll go ahead and put those variables in there so you can see where they come from. So instead of y versus x, it's velocity versus time, and that's the slope right there. And lo and behold, look at that. The slope is negative 1.5, and the slope, if you recall, of a velocity time graph is acceleration. Oh my goodness, look at that. And look at the y-intercept. The y-intercept is 25.3. The y-intercept is the velocity when time is 0. It's also known as the initial velocity. Look at that, 25.3. Oh, I'm giddy with excitement. Okay, once we have this graph done, it's really fast to do the next graph. We just copy that whole graph, paste the whole graph. And this is going to be position versus time, or displacement versus time of a simulated car. Now I have to get rid of this. I can actually delete the trend line. Okay, so now if I click on any of the data points here, I can see that I'm graphing time over here and velocity. All I have to do is grab the box, the velocity box, and move it where I want to. Now it's position versus time. All right, so this is position versus time, and of course we need to change this to position. Position makes a little bit more sense for reasons that may not be well understood by some introductory students. That's okay. And if we wanted to fit this curve, we could fit a trend line here. There it is. we know that it's going to be polynomial, and I know it's going to be second order. Okay, so I'm going to fit the equation, display r squared value. There. And you might have recalled this number right here is 1/2 of the acceleration. So if you double it, it's the acceleration. Yeah, that works. This number here is the initial velocity, and this number here is the initial position, which should have been close to 0. All right, well, that is basically it in a nutshell. I hope this was informative, and let me know with your comments what you think about it. Thanks for watching, and see you next time.